This is my lab for circuits and capacitors. My name is Daniela. So in this lab, we're using an online simulator to create circuits to predict behaviors of circuits in parallels and in series. We use ammeters and voltmeters to measure and give experimental data. And in this lab, we took the slope equation form to calculate the ln linearized formula to get the RC value equal to 3.03. We will also be looking into Ohm's law, energy conservation and charge conservation, resistor, capacitor, RC circuits, and time dependency. So some of the relevant formulas, we have the energy conservation equation, which is the change in voltage capacitor plus the change in voltage resistor is equal to 0. And this is the equation for the capacitor, which is change in V is equal to Q over C. And we calculated the RC in this lab by getting the change in V is equal to the change in V naught over RC. And we linearized it by taking the ln of this function. So some of the basics of the experiment, we set up in the simulator and we got the I1 is equal to I2, which is equal to 0.02 amps, which is what we were supposed to do in the lab. And if the ammeter was connected backwards, it would still have a charge of 0. The voltage of this current is 3 volts overall because we had 2 batteries and each of the battery was 1.5 volts. And in this closed circuit, we had the resistor with 47 ohms is equal to negative 0.959 volts, and the resistor of 100 ohms is equal to negative 2.041, which is equal to negative 3. So the 3 volts from batteries cancels out with the resistors. So in our graph in the observations, so we're looking at how the battery raises the potential. The wires are ideal, so they should have no resistance. The resistors lower the potential, and that's why it's negative in the graph. Ammeter should supposed to be ideal and have 0 resistance, so it should have 0. And so we calculated, just to double check our work to make sure that the 0.959 divided by the 0.2 would give us the 47 ohms, just to make sure that it is correct. And we did that for both of the resistors, the wire, and the ammeter. So here we are looking at part B. And in part B, there was a few different questions in the observations about a bulb, and if it was connected to the battery in the RC circuit, we know that it'd be very bright and slowly dim when it's turned off. If it's connected to the charge capacitor, it would be the same as before, but be very bright and then slowly dim. And then things like that. So those were some of the observations that we had in the lab. So on the right, we have a table with all of our experimental data that we got from our simulation. And on the left is the graph of the raw data from our experimental data. Then we take the ln of it to linearize the whole function and get a negative linear line. And we get time versus the ln of the change of potential difference. And so by applying the formula that we had in our first formula, on our second slide, we get our slope to be negative 0.3379, and then to get our RC value, we do negative 1 divided by the slope, negative 0.3379, and we get our RC value to be 3.03. So here are some of our what if questions. What if you're doing the lab in real life and you use an actual ammeter instead of an ideal simulated ammeter? What's the difference about a real ammeter, and how would it affect the circuits you hooked it up to? So an ammeter has some resistance in real life, while in the lab there is 0 resistance. This means that the results that we would have gotten in real life would be lower because in real life there is resistance, so our data would be lower. So what if you were doing the lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit, how quickly would our ideal model predict the capacitor to reach full charge? Will this prediction happen in real life? So a real capacitor would be charged instantly in the lab, but in real life, since there is resistance in the wires and in the battery, it wouldn't be charged instantly like it would be in the lab. Thank you.